Jai Hind to everyone. This is Ritika Dhyani from CSE department in AKGEC. Today's the topic of my lecture is lattice and its types. Basically, this is in this presentation what we are going to cover is what is a lattice, how we can find a particular structure is a lattice or not, and the different types of lattice. So the first thing is what is lattice? It is a poset in which every pair of element has both a least upper bound and a greatest lower bound. What is a poset first of all? If we consider a relation R on a particular set S, then the relation must satisfy these three properties, which is first one is reflexive, second is antisymmetric, and the third one is transitive. If the particular relation follows these three properties, then it is called partial order relation, and the set together with this relation is called poset and is denoted by this particular symbol S and the less than equals to sign. First of all, before moving on to the how we can find a particular structure is a lattice or not, we need to know what is upper bound and what is lower bound. Upper bound, it is an element which is greater or equal to all elements in a subset of poset, and the lower bound is is an element which is smaller or equal to all elements in a poset. What does it means? For example, if we consider this structure then if for this particular element, these particular elements, this particular pair, what we can say the upper bound is, if we move towards the upward direction, then we will be reaching G and we will be reaching H. Then both these elements will be the upper bound for this particular pair. If we talk about lower bound, then what is the lower bound? If we move downwards from these two particular elements, we reach C and we reach A. C and A. What does it mean? That if before finding the upper bound and lower bound, if we talk about particular pair, then from those pair we need to go upward direction for the upper bound, and from those pair we need to go downward direction from that particular pair. If we talk about the greatest lower bound, then the greatest lower bound for this particular pair will be C, because if we compare C and A, then the C is on the upper level. So the greatest lower bound will be the C, and the least upper bound will be, if we talk about G and H, then which level is lower? G. So the least upper bound will be the G. So in this way we can find the upper bound, lower bound, greatest lower bound and the least upper bound. The two operations that we can perform on lattice is, first one is join. The join of two elements is their least upper bound. If we perform this operation, we can find the least upper bound. It is denoted by the symbol V, and if in a particular poset only least upper bound exists, then that particular structure is known as join semi-lattice. The second one is meet. Meet of two elements is their greatest lower bound. It is denoted by the symbol inverted V. If in a poset for every pair of element only the greatest lower bound exists, then it is known as the meet semi-lattice. Moving on to some examples. First one, if we talk about this example here, each first of all we need to find if it is a lattice or not. For lattice, if the structure has single top and single bottom, then we can say this particular structure is a lattice. So this is lattice. For this particular structure, we are having two bottoms. So of course this is not a lattice, but we can say, because these two structures, these two elements A and B both does not have greatest lower bound. As we can see, from A and B we cannot move downwards, so there is no element which we can reach from A and B. So so there is no greatest lower bound. So this will be this lattice will be joint semi lattice, because for each pair you can find the least upper bound but you cannot find the greatest lower bound. Moving on to the third example, here we can see there are two tops and single bottom. Single bottom means for each pair we will be having greatest lower bound, but because there are two tops, so therefore least upper bound does not exist for the elements E and F. E and F. So what is this lattice? This is meet semi lattice. Then moving on to the next example, we are having single top and single bottom, but still it is not a lattice, because for this pair C and B, if we talk about C and B, we will be having upper bounds D, E and F. D, E and F. What does it mean? That by moving upward direction we can reach C or D from both C and B. So there will be three upper bounds. Now we can see which least upper bound is here. There is no least upper bound, because these two pairs D and E are non-comparable. They are on both the same level, so we cannot compare which will be the least upper bound. So this is not a lattice. These will be the solution that we have covered in the previous slide. Next, moving on to the types of lattice. We will be covering these 5 lattices. First one is complete, second is bounded, third is complemented, fourth one is distributive, and the fifth one is modular. First of all, what is a complete lattice? A partially ordered set is a complete lattice if every subset of L has both greatest lower bound and least upper bound. What does it mean? That if in every pair in a lattice must have the greatest lower bound and the least upper bound for each pair, then it is known as complete lattice. Otherwise, it is not a complete lattice. What does it mean? If we talk about example, here we are taking Z. Z is a set of integers under the relation less than equals to. For here, if we are having finite set, how X is an element such that it is greater than equals to -2 but less than equals to 2. Then we are having these elements in the set. If we draw the hash diagram for this particular set under this relation, then it will be like something like this. Here the least upper bound and the greatest lower bound exist, right? But if we talk about the infinite set, if the set has something like X is greater than equals to 2, then the set will be having 2, 3, 4 and so on. So then this will not be the complete lattice, because there will be no greatest lower bound exist. Second one is bounded lattice. If for a lattice both greatest element and the least element exist, then it is known as the bounded lattice. What is the greatest element or the least element? First, the greatest element. It is the maximal element which should be unique if we consider it as a greatest element. In the topic POSET, we know that there will be multiple maximal elements exist, but if we talk about greatest element, then only one maximal element should exist. Same case is with the least element. One minimal element, if there is one minimal element, then that element is known as least element. For example, here the greatest element is, of course, this pair, this element, and the least element is this. Hence, it is a bounded lattice. But in case of infinite series, there is no greatest element or the least element. So, it is not possible to find maximum or minimal in this case. Hence, it is not a bounded lattice. Third one is your complemented lattice. If lattice is bounded and every element in a lattice has a complement, then it is known as complemented lattice. Firstly, the lattice needs to be the bounded lattice. That means there must exist one greatest element and one least element. Secondly, every element in the lattice must have complement. What does it mean to have a complement? For example, let L be a bounded lattice and let's say an element of L be A. Then if X be the complement of A, then this operation, this is the join operation, join the A with it, join with its complement, it will result to greatest element. Similarly, if A along with its complement we perform meet operation, then it should result in least element. For example, here if we have here the greatest element is D and least element is your A. So if we talk about finding the complement of A, then A join which element results to D. Of course, we need to join A with D to get the result D. And then A meet which same element, it should result to A only, least element. So A complement is D. Similarly, D's complement is A. Moving on to the B, finding B's complement. B join which element results to D. B से अगर हम if we move upward direction, then from which element if we move upward, we will be reaching D. Of course, from C. So B join C will be your the greatest element, and performing meet operation with the same element, it should result to A. Of course, moving in a downward direction, we reach A. Here, so the B's complement is C and C's complement is B. In this way, we can find the complement. Taking next example, here the greatest element is F and the least element is A. Least element is A. If we need to find the complement of B, then we can check it with B union join C. It results, we can move upward from both and we reach to a particular common element which is F, and F is the greatest element also. So this is satisfying the condition for complemented lattice. Same, if we move downwards from B and C, we reach A, which is the least element. So complement of B can be C. But there is one more complement of B. If we check B join E, in this case also we will be reaching F and in upward direction and A in downward direction. It is also satisfying the conditions for complemented lattice. Hence, E is also the complement of B. So, in a complemented lattice, a particular element can have more than one complement. For any complemented lattice, the complement of an element need not to be unique. Fourth one is your distributive lattice. A lattice L is called distributive lattice if for any elements A, B and C, it satisfies the distributive properties. If any of the three elements does not satisfy these two properties, then it is called non-distributive lattice. What does it mean? Let's take it with an example. Here, if we take 2, 3 and 5, these three elements as A, B and C. First, we can check 2 meet B, 3 join 5. LHS we are performing. Then here, if from 3, first we need to perform this operation. From 3, we move upward and we will be reaching 30. So, 3 join 5 is 30. And 2 meet 30 is definitely we are moving downwards from both the elements. We will be reaching the same element 2 here. If we take the RHS, then 2 will meet 3, join 2 meet 5. Here 2 meet 3, 2 meet 3, that means we need to move downward direction from both the elements. We will be reaching 1. 1 join 2 meet 5. From 2 we need to move downward, and from 5 we need to move downward. We will be reaching 1. Here the join 1 with the same element is also 1. So of course, not 1, this will be like, so LHS is not equals to RHS here. So this is not a distributive lattice. Also the hint, which it is not possible for us to check it for every 3 elements. So there is a hint. If lattice L is said to be distributive, if every element L in particular lattice has at most 1 complement. It is also possible that a particular element does not have a complement in case of distributive lattice, but it cannot have more than 1 complement. This is the condition. Last one is your modular lattice. A lattice is called modular lattice if this particular condition A join B meets C equals to changing the brackets A join B with meets C whenever A is less than equals to C. What does it mean? It means the level of A must be below the level of C. For example, if we take here any 3 elements like B, C and D, or B, D and C, right? If we take these 3 elements B, D, C, in this case we know the level of B is less than level of C because C is on the below level than C. So we can take this example B, D, C. For this we can check this property B join D meet C. For LHS, firstly B join D meet C, that means we need to move downwards from both the elements. So from we are moving downwards and we reach A as a common point, then B join A. B join A will be, from A we need to move upward and we reach B. So the join is B. Let's take RHS and check B join D meet C. B join D. B join D, that means from B we need to move upward direction, and from D also we will be reaching to point E. E meets C. E meets C will be, if we move downwards from E, we will be reaching the point C. So, if they are not equal, then it is not a modular lattice. In case these 2 elements, the results is equal, then it is known as the modular lattice. Thank you.